Hi, hello, welcome. This is Tej Bhargav. Today I am here to explain you about the model matrix. I am bearing the roll number 22951A67F2 with this going with the subject LAC, that is linear algebra and calculus. Matrices. First of all, what is a matrix? A matrix is a rectangular arrangement of elements in rectangular rows and columns. Like it contains row 1, row 2, row 3, column 1, column 2, column 3. Okay. Next, a matrix of m rows and n columns is called a matrix with dimensions m into n. For example, when we are getting into the dimension like 2, minus 3, 4, minus 1, 1, 2, 1 by 2, 5, then the first, coming to the first example, there are 2 rows and 3 columns. So the dimensions of the matrix is 2 by 3 matrix. Next, going to the second example, it is 3 by 3 matrix. Like there are 3 rows and 3 columns, like minus 3, 8, 9 is first row. 1 pi minus 2, 5 is the second row. Minus 6, 7, 8 is the third row. And minus 3, pi, 6, 8, minus 2, 7, 9, 5, 8 are row 1, row 2, row 3 respectively. So hence it is called a 3 by 3 matrix. Next 10 minus 7. There are 2 rows and 1 column, and hence it is called, hence its dimension is 2 into 1. Next, here as it contains only 1 column, this matrix is also known as column matrix. The matrix which contains only 1 row in it is known as column matrix. Next, minus 3, 4. A matrix which contains only 1 row is called row matrix. Hence is the fourth one is an example of row matrix. Next, eigenvectors and eigenvalues. A non-zero vector x is an eigenvector or characteristic vector of square matrix A if there exists a scalar such that Ax is equals to lambda x. Then lambda is an eigenvalue or characteristic value of A. A non-zero vector cannot be an eigenvalue, like even though A is equals to 0. A is equals to 0. A0 is equals to lambda 0, but lambda is equals to 0 can be a eigenvalue. Example. So x is equals to 2, 1 is an eigenvector for A is equals to 2, minus 4, 3, minus 6. Solution. Ax is equals to 2, minus 4, 3, minus 6, 2, 1, 0, 0. But for lambda is equals to 0, lambda x is equals to 0 into 2, 1 is equals to 0, 0. Thus x is an eigenvector of A and lambda is equals to 0 is an eigenvalue. Let x be an eigenvector of the matrix A, then there must be an eigenvalue lambda such that Ax is equals to lambda x, or equivalently Ax minus lambda x is equals to 0. A into A minus lambda into I is equals to x is equals to 0. If we define a new matrix B is equals to A minus lambda I, then Bx is equals to 0. If B has inverse, then X is equals to B inverse 0 minus is equals to 0. But an eigenvector cannot be 0. Thus, it follows that X will be an eigenvector of A, and if and only if B does not have inverse, or equivalently that B or 0, or that A minus lambda I is equals to 0. This is called the characteristic equation of A. Its roots determine the eigenvalues of A. Next, eigenvalues example. Example 1. Find the eigenvalues of A is equals to 2 minus 12, 1 minus 5. Lambda I minus A is equals to lambda minus 2, 12 minus 1, lambda plus 5. Lambda minus 2 into lambda plus 5. Minus of minus 12 becomes plus 12 is equals to lambda square plus 3 lambda plus 2 is equals to lambda plus 1 into lambda plus 2. Two eigenvalues are minus 1, minus 2. Note, the roots of the characteristic equations can be repeated. that is lambda 1 is equals to lambda 2 is equals to lambda k. If it happens, the eigenvalue is said to be multiplicity of k. Example 2. Find the eigenvalues of A is equals to 2, 1, 0, 0, 2, 0, 0, 0, 2. Lambda I minus A is equals to lambda minus 2 into minus 1, 0, 0. Lambda minus 2, 0, 0, 0. Lambda minus 2 is equals to lambda minus 2 whole cube is equals to 0. Lambda is equals to 2 is an eigenvector of multiplicity 3. To each distinct eigenvector of matrix A, there will be corresponding at least one eigenvector, which can be found by solving the appropriate set of homogeneous equations. If lambda I is an eigenvalue, then corresponding eigenvector xi is the solution of the A minus lambda I into xi is equals to 0. Example, lambda is equals to minus 1 into I minus A is equals to minus 3, 12, minus 1, 4, 1, minus 4, 0, 0. X1 minus 4x2 is equals to 0. X1 is equals to 4t, x2 is equals to t. X1 is equals to x1, x2 is equals to t of 4, 4, 1. T is not equal to 0. Lambda is equals to minus 2. Minus 2 into I minus A is equals to minus 4, 12, minus 1, 3, 1, minus 3, 0, 0. X2 is equals to x1, x2 is equals to s1, s of 3, 1. Example 2. Find the eigenvectors of A is equals to 2, 1, 0, 0, 2, 0, 0, 0, 2. Recall that lambda is equals to 2 is an eigenvector of multiplicity 3. Solve the homogeneous linear system represented by 2I minus minus A into x is equals to 0, minus 1, 0, 0, 0, 0, 0, 0, 0 into x1 into x2 into x3 is equals to 0, 0, 0. Let x1 is equals to s, x3 is equals to t. The eigenvectors of A of lambda is equals to 2 are of the form x is equals to x1, x2, x3 is equals to s o t is equals to s of 1, 0, 0 plus t into 0, 0, 1 s and t not both 0. Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic equation. Let A is equals to Aij into n by n matrix be a square matrix. Then A is equals to A11, A12, A1n, A21, A22, A2n up to AN1, AN2, ANn into n into n matrix. Let the characteristic polynomial of A be phi of lambda, then phi of lambda is equal to A minus lambda I, A11 minus lambda, A12, A1n, A21, A22 minus lambda, A2n, AN1, AN2, ANn minus lambda. The characteristic equation is A minus lambda I is equal to 0. Verify Cayley-Hamilton theorem for the matrix A is equals to 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2. Hence compute A inverse. Solution. The characteristic equation of A is A minus lambda I is equals to 0. That is 2 minus lambda minus 1, 1 minus 1, 2 minus lambda minus 1, 1 minus 1. 2 minus lambda is equals to 0 or lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0 on simplification. To verify Cayley-Hamilton theorem, we have to show that a cube minus 6a square plus 9a minus 4i is equals to 0. Now a square is equals to 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2, 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2 is equals to 6 minus 5, 5 minus 5, 6 minus 5, 5 minus 5, 6. A cube is equals to a square into a. 6 minus 5 minus 5 minus 5, 6 minus 5, 5 minus 5, 6 into 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2 is equals to 22 minus 22 minus 21 minus 21, 22 minus 21, 21 minus 21, 22. A cube minus 6a square plus 9a minus 4i is equals to 0. 22 minus 22 minus 21 minus 21 22 minus 21 21 minus 21 22 minus 6 into 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6 plus 9 into 2 into minus 1 1 minus 1 2 minus 1 1 minus 1 2 minus 4 into 1 0 0 0 1 0 0 0 1 is equals to 0 0 0 0 0 0 0 0 0 is equals to 0. This verifies Cayley-Hamilton theorem. Now, pre-multiplying both sides of 1 by A inverse, we have A square minus 6A plus 9I minus 4A inverse is equals to 0. 4A inverse is equals to A square minus 6A plus 9I. 4A inverse is equals to 6 minus 5, 5 minus 5, 6 minus 5, 5 minus 5, 6 minus 6 into 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2 plus 9 into 1, 0, 0, 0, 1, 0, 0, 0, 1 is equals to 3, 1 minus 1, 1, 3, 1 minus 1, 1, 3. Therefore, A inverse is equals to 1 by 4 into 3, 1 minus 1, 1, 3, 1 minus 1, 1, 3. Diagonalization of a matrix. Diagonalization of matrix A is the process of reduction A to a diagonal form. If A is related to D by similarity transformation such that D is equals to M inverse AM, then he is reduced to diagonal matrix D through model matrix M. D is also called a spectral matrix. Reduction of matrices to diagonal form. If a square matrix A of order n has linearly independent eigenvectors, then matrix B can be found such that P inverse AB is a diagonal matrix. Note, the matrix B which diagonalizes A is called the model matrix of A and is obtained by grouping the eigenvectors of A into square matrix. Similarity of matrices. A square matrix B of order n is said to be similar to a square matrix A of order n if B is equals to M inverse AM is for some non-singular matrix M. This transformation of matrix A by non-singular matrix M to B is called similarity transformation. Note, if the matrix B is similar to matrix A, then B has the same eigenvalues as A. Example, reduce the matrix A is equals to 1 minus 1, 2, 0, 2 minus 1, 0, 0, 3 to diagonal form by similarity transformation. Hence, find A cube. Solution. Characteristic equation is 1 minus lambda minus 1, 2, 0, 2 minus lambda minus 1, 0, 0, 3 minus lambda 0 is equals to 0. Lambda is equals to 1, 2, 3. Hence, eigenvalues of A 1, 2, 3 corresponding corresponding to lambda is equals to 1. Let x1 is equals to x1, x2, x3 be the eigenvectors. Then a minus I into x1 is equals to 0, 0, minus 1, 2, 0, 1, minus 1, 0, 0, 2. X1, x2, x3 is equals to 0, 0, 0. Minus x2 plus 2x3 is equals to 0. X2 minus x3 is equals to 0. 2x3 is equals to 0. X1 is equals to k. X2 is equals to 0. X3 is equals to 0. Where x1 is equals to k1 is nothing but an arbitrary constant. corresponding to lambda is equals to 2. Let x2 is equals to x1, x2, x3 be the eigenvector. Then a minus 2i into I into x2 is equals to 0, minus 1, 0, 2, 3, 0, 0, minus 1, 0, 0, 1, x1, x2, x3 is equals to 0, 0, 0, minus x1, minus x2 plus 2x3 is equals to 0, minus x3 is equals to 0, x3 is equals to 0, x1 is equals to k2, x2 is equals to minus k2, x3 is equals to 0, x2 is equals to k2 into 1 into minus 1 into 0. Corresponding to lambda is equals to 3. Let x3 is equals to k1. Let x3 is equals to x1, x2, x3 be the eigenvector. Then a minus 3i into x3 is equals to 0. Minus 2, minus 1, 2, 0, minus 1, minus 1, 0, 0, x1, x2, x3 is equals to 0, 0, 0. Minus 2x1 minus x2 plus 2x3 is equals to 0, minus x2 minus x3 is equals to 0, x2 is equals to k3, x3 is equals to minus k3, x1 is equals to minus 3 by 2 k3, x3 is equals to k3 into 3 minus 2, 2. Hence, model matrix is M is equals to 1, 1, 3, 0, minus 1, minus 2, 0, 0, 2. Mod M is equals to minus 2. Adjoint M is equals to minus 2, 2, minus 2, minus 2, 1, 0, 2, 2, 0, 0, minus 1. M inverse is equals to adjoint M by mod M. Det M 1 is equals to 1, 1, minus 1 by 2, 0, minus 1, minus 1, 0, 0, 1 by 2. M inverse A M is equals to 1, 1, minus 1 by 2, 0, minus 1, minus 1, 0, 0, 1 by 2. 1, minus 1, 2, 0, 2, minus 1, 0, 0, 3, 1, 1, 3, 0, minus 1, minus 2, 0, 0, 2, 1, 0, 0, 0, 2, 0, 0, 0, 3. And since D is equals to M inverse AM, A is equals to MD M inverse, A square is equal to MD M inverse into MD M inverse is equals to MD square M inverse. Similarly, A cube is equals to MD cube into M inverse is equals to 1, 1, 3, 0, minus 1, minus 2, 0, 0, 2, 1, 0, 0, 0, 8, 0, 0, 0, 27, 1, 1, minus 1 by 2, 0, minus 1, minus 1, 0, 0, 1 by 2. A cube is equals to 1, minus 7, 32, 0, 8, minus 19, 0, 0, 27. Orthogonal transformation of a symmetric matrix to diagonal form. A square matrix A with real elements is said to be orthogonal if A into A dash is equal to I is equal to A dash into A. But A into A inverse is equal to I is equal to A inverse A is equal, follows that A is orthogonal if A dash is equal to A inverse. If A is real symmetric matrix, then eigenvectors of A will not be linearly independent but also pairwise orthogonal. If we normalize each vector and use them to form the normalized model matrix N, then it can be proved that N is an orthogonal matrix. The similarity transformation M inverse AM is equals to T takes the form N dash A N is equals to T since N inverse is equals to N dash by property of orthogonal matrix, transforming A into D by means of transformation N dash An equals to D is called the orthogonal reduction or orthogonal transformation. Note to normalize eigenvector XR, divide each element of XR by the square matrix of the sum of the squares of all the elements of X. Diagonalize the matrix A is equals to 2, 0, 4, 0, 6, 0, 4, 0, 2 by means of orthogonal transformation. Solution. Characteristic equation of A is 2 minus lambda 0, 4, 0, 6 minus lambda 0, 4, 0, 2 minus lambda is equals to 0. 2 minus lambda into 6 minus lambda into 2 minus lambda minus 16 into 6 minus lambda is equals to 0. Lambda is equals to minus 2, 6, 6. When lambda is equals to minus 2, let x1 is equals to x1, x2, x3 be the eigenvector, then a plus 2I into x1 is equals to 0. 4, 404 into x1 x2 x3 is equals to 0 0 0. 4x1 plus 4x3 is equals to 0. 8x2 is equals to 0. 4x1 plus 4x3 is equals to 0. x1 is equals to k1, x2 is equals to 0, x3 is equals to minus k1. x1 is equals to k1 into 1 0 minus 1. When lambda is equals to 6, let x2 is equals to x1 x2 x3 be the eigenvectors. A minus 6i into x2 is equals to 0 minus 4 0 4 0 0 0 4 0 minus 4 x1 x2 x3 is equals to 0 0 0 minus 4x1 plus 4x3 is equals to 0. 4x1 minus 4x3 is equals to 0. Therefore, x1 is equals to x3, x2 is an arbitrary constant. X2 must be so chosen that x2 is equals to x3 are orthogonal among themselves, and also each is orthogonal with x1. Let x2 is equals to 1 0 1. Let x3 is equals to alpha beta gamma. Since x3 is orthogonal to x1, lambda minus gamma is equals to alpha minus gamma is equals to 0. x3 is orthogonal to x2. Lambda plus alpha plus gamma is equals to 0. Solving 4 and 5, we get alpha is equals to gamma is equals to 0. B is an arbitrary. Taking B is equals to 1. X3 is equals to 0, 1, 0. Therefore, model matrix M, the model matrix is M is equals to 1, 1, 0, 0, 0, 1, minus 1, 1, 0. The normalized model matrix is N is equals to 1 by root 2, 1 by root 2, 0, 0, 0, minus 1, minus 1 by root 2, 1 by root 2, 0. D is equals to N dash A, N is equals to 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 1 by root 2, 0, 1 by root 2, 0, 1, 0, 2, 0, 4, 0, 6, 0, 4, 0, 2, 1 by root 2, 1 by root 2, 0, 0, 0, 1, minus 1 by root 2, 1 by root 2, 0. D is equals to minus 2, 0, 0, 0, 6, 0, 0, 0, 6, which is the required diagonal matrix. So far, whatever we discussed is like model matrix, definition of matrix, examples of the matrix, eigenvalues and eigenvectors, examples of those, and Cayley Hamilton, which is most important, like every square matrix satisfies its own characteristic equation. And after that, model matrix and diagonalization of matrix and reduction of matrix to diagonal form. And we looked after into examples and orthogonal transformation of symmetric matrix to diagonal form. And so far, everything we have been discussed. Okay, I thank you for giving this an opportunity. Hope so you are clear with the model matrix.